Okay, in this class, we study inertia tensor calculation for various cases. First, we consider the computation of inertia tensor for a uniform cube of mass m with side A. The density of the uniform density will be the mass divided by the volume, so that is m over a cube. The density multiplied by the volume differential will be the differential of the mass. The inertia tensor, ij element of the inertia tensor, can be computed by integrating over the volume with the density multiplied by this tensor structure. We can check the mass of the cube can be reproduced by computing this one. The range of the x, y, z integral will be from 0 to a, and density will be mass divided by a cube. The integration is over this space. That is a cube. Thus, the result will be the mass. So we have a correct normalization for the density. The first 1 element of the inertia tensor can be computed by multiplying the density and volume differential multiplied by 1 element will be computed as x squared y squared z squared minus x squared, so y squared plus z squared integration. First, if we integrate over z, that results in 1/3 a cube and y squared a. Then we can integrate over y to have 1/3 of a cube multiplied by a, and y integration of this constant will be multiplied the same as the multiplication of a. At the end, we have a constant integration over x, so this integral will be just a. The result is the 2/3 of ma squared. In the case of 2 element, we have x squared z squared integral. The same procedure can be done for this integral. The result is 2/3 of ma squared. The system is a symmetry on the exchange of x, y, z direction. That is a symmetric form, so all the diagonal elements must be the same. Next, we consider the off-diagonal element 1, 2. That is the same integral measure, and the integrand will be minus x, y. The integral over x and y can be factorized, and the z integral is trivial. It's a. This integral is 1/2 a squared. This one is 1/2 a squared too. The result is minus 1/4 ma squared. In the same manner, I13 is the integral of minus zx. I23 is integral of yz, negative sign. The same structure. The result, all of the off-diagonal elements will be 1/4 of ma squared. So with the over factor ma squared, we have diagonal elements all the same, so 2/3, and off-diagonal elements are minus 1/4. The inertia tensor depends on the choice of the axis, the reference frame axis. In case we have the origin is placed at the center of mass, even though the density is the same as before, the integral have the different ranges. The same cube with the side A, the integral over x will be not 0 to a, but minus 1/2 a to plus 1/2 a. YZ integral has the same range. We have an integrand y squared z squared for the 1 element. we find that this is an even function of z. The integral over z will be, this is a minus 1/2 a, 2 plus 1/2 a, an even function. So twice the integral from 0 to 1/2 a. The result is y squared is constant for z. This integral is 1/2 a. And this factor of 2 is moved here. And this t integral is 1/3 of 1/2 a cube. Next, we carry out the y integral. This is again even function with respect to y. So we have factor of 2 moved to here to have factor of 4m, and integral is revised from 0 to 1/2 a. The result is y squared. This is integral. This integral gives 1/3 of this 1/2 a's cube and half of a, and this is constant, so we just multiply 1/2 a. The final stage, this x integral is trivial because it is constant, so this becomes a. The final result is 1/6 of ma squared for the 1, component. As we notice, this x, y, z axis, we have a symmetry of exchanging x, y, z axis, so all of the diagonal component will be 1/6 of ma squared. As a result, the 2, 2 and 3, 3 are all 1/6 a. What about 1, 2 element? 1, 2 element has integrand x and y, and x integral, y integral. Both of them are odd function in the range of minus something to plus something. So odd function integral in this range must be 0. So off diagonal I12 equals 0. Because of the symmetry, we have all the off diagonal components to be 0. So this is proportional to the identity, and we remember that identity matrix is invariant under rotation. Thus, what we have found is the inertia tensor in the body frame whose central mass is at the origin is proportional to the identity matrix. It has already been diagonalized, and we say the diagonal element in the diagonal matrix for the inertia tensor is said to be principal values. In this case, we have all three principal values the same. The same principal values states that we have triply degenerate states. If inertia tensor is diagonalized, all of the unit vectors 1, 0, 0, and 0, 1, 0, and 0, 0, 1 will be the principal axis, corresponding principal axis, and all of the eigenvalues are identical. We say that the unit vector along the principal axis are all linearly independent, and they are all orthogonal to each other. Therefore, if I combine all three pieces, they are orthogonal with the unit normalization, then direct product of each basis vector summed over these three states will be identity matrix. This is completeness relation we just have studied in the previous chapter. Let us consider next on the rotation of an inertia tensor. this is the three-dimensional object, and the rank to Cartesian tensor follows the rotational property. In case we have a vector transformation x prime equals lambda x, then the Rx for the rotation matrix, in that case the rank to Cartesian tensor transforms like this. Suppose that our rotation is about the z-axis about the finite angle theta, then the rotation matrix is written in this form. We substitute this R matrix R and the transpose in here, and we can read off the 1 1 element as it is. This is the first row of the rotation matrix, and this is the first column of the transpose of this matrix. So the first row of this R transpose will be there. So after the long calculation, we find that the 1 1 element has the dependence on the angle theta. Just like this, we can compute 1 2 element in this way and 1 3 element this way, and we can make use of the symmetry. The inertia tensor is we learned that inertia tensor is a symmetry on the exchange of the row and column, and of diagonal elements, and all of the diagonal elements for 2 2 and 3 3 elements can be obtained in this way. Alright. So we have C minus S0. C is a cosine theta. S stands for the sine theta. So let us multiply this matrix. This matrix is here. Because this is complicated form, we have diagonal elements will be alpha, which is the 2/3, and the off diagonal elements will be beta, and beta is a minus 1/4. Alright, multiply this column vector to the inertia tensor, and over vector is placed in here, ma squared. We multiply this one to here to find alpha cosine theta minus sine beta, and the next one is a beta cosine and alpha sine minus sine, and the third one is all beta, so beta is factored out, cosine minus sine, and then we multiply this one to this row vector to have cosine alpha minus sine beta, okay, and minus sine cosine beta minus sine alpha. The next one is 0. If we factored out the alpha dependent piece, this is cosine squared, alpha dependent piece plus sine squared, and this is 1. Next, beta dependent first term is minus cosine sine and minus cosine sine, so we have minus 2 cosine sine beta. We substitute alpha and beta written in here to find out that the 1 1 element is ma squared multiplied by 2/3 plus 1/2 cosine and sine. As we have seen like this, the 1 1 element is dependent on the angle. Suppose that it is rotating with the constant angular velocity omega. In that case, this one becomes a cosine omega t sine omega t. Thus each element of the inertia tensor depends on time, unless we use a body frame. The body frame, the main reason why we use the body frame as a reference frame to compute the inertia tensor is inertia tensor becomes constant. However, if we compute the inertia tensor in such a way, the frame is fixed and it is rotating, the inertia tensor depends on time. So complication will be very, very complicated. That's the reason why we use the body coordinate system. One two element can be computed with the first row of rotation matrix and second column of the transpose of the rotation matrix. The final result will be obtained with a sine square, cosine square minus sine square style, that is a cosine 2 theta dependence that appears here. In the calculation of I prime 1 free element, then we multiply the first row of the rotation matrix and third column of the transpose of the rotation matrix. The final result will be depending on the difference of cosine and sine. And two free element and two free elements are obtained in here. In summary, the theta dependence appears as a 2/3 plus 1/2 cosine sine, 2/3 minus 1/2 cosine sine, and cosine 2 theta, difference of sine and cosine, and sum of sine and cosine. So it becomes quite complicated. Now let us consider the parallel axis theorem. Just like what we have proved for the parallel axis theorem in the previous, the last class, the inertia tensor for this case can be computed in terms of the inertia tensor whose origin, whose origin is at the center of mass, and the difference will be expressed in terms of the delta parallel. Delta parallel is the constant tensor that depends on the distance, this displacement vector d, that is, there used to be the center of mass is here. Center of mass is now moved to the central point at the center of mass, but origin is in here. So we have d vector like that. That d vector is just 1/2 of a multiplied by 1, 1, 1. Alright, so the 1 element is this constant tensor delta parallel can be computed. So 1, this is 1. D square is, we have 1/2 d, 1/2 a squared, that is a square over 1/4 a squared. And we have d squared, this one 1 squared plus 1 squared 1 is 3, and minus 1. Okay, because we have factored this 1/2 a out. The final result is that we have 1/2 ma squared for that 1 element. Because of the symmetry, we have 2 element and the 3 element all the same as 1/2 ma squared. What about 1 2 element? 1 2 element, this one vanishes and this one survives. That is just the square of this and negative sign on it. Therefore, we have m times 1/4 a squared. And because of the symmetry, we have this is the original value for the evaluated one at the center of mass. And the difference, this delta, has all the diagonal pieces with 1/2 ma squared. All the off diagonal pieces we have minus 1/4 ma squared. Ma squared is factored out. If we add these two components, we have the final result for the I prime. But we remember that this I prime is the 2/3, 2/3, 2/3, and of diagonalism minus 1/4, and this result exactly reproduced the previous result. Okay. Next, we consider diagonalization. We have all 9 non-vanishing elements, and if I want to diagonalize this matrix, we first introduce the eigenvalue problem. We have over a factor, ma squared common factor, so we scale out the dimensionful quantity as ma squared and find out the eigenvalue, relative eigenvalue normalized by ma squared. The solution of this lambda is to be multiplied to find out the principal value for the inertia tensor, and the corresponding eigenvector can be obtained. And that eigenvector is the vector along the principal axis, and we can normalize the eigenvector as a unit normalization. Then we have the orthonormal basis that whose axes are parallel to the coordinate system in which the matrix is diagonalized. First, in order to have this non-vanishing eigenvector, we need to find out the cyclic equation. This I minus ma squared lambda identity matrix psi equals 0. In order to have this non-vanishing value for psi, the determinant of this one must vanish, because if the determinant is non-zero, then there is an inverse matrix of this. If I multiply the inverse matrix to here, we find the psi equals 0. That means psi has a trivial solution. All components are vanished, but we don't want to do that. And there must exist non-vanishing psi. In that case, the determinant must vanish so that it does not have any inverse matrix. We substitute these values in here, and because the calculation is too busy, let me write this one, substitute this one as alpha. All the diagonal elements are alpha, 2/3 minus a, lambda. And all the off-diagonal elements, that is minus 1/4, will be the beta. So let us compute the determinant of this. Determinant of this is, let me choose the elements of the first row. The first row, alpha, this one, and remove this column and row. Remaining piece will be this 2x2 matrix. Copy this 2x2 matrix and find out the determinant. The second one is beta, and we have even, odd, even. So minus beta. Sign, permutation sign minus is appearing here, and remove the row and column passing this element. Then we have beta beta and the beta alpha copied. The third piece is the beta, and we have even, odd, even, so we have plus beta, and remaining the 2x2 matrix will be like that. This is beta beta alpha beta. Okay. We can expand this one. This one is alpha squared minus beta squared. And this is alpha beta minus beta squared. And beta squared minus alpha beta. And all the detailed calculation shows that it's factorized, so that we have alpha minus beta squared plus alpha plus 2 beta. The solution for having vanishing determinant is alpha equals beta is doubly degenerate. And we have alpha equals minus 2 beta style. So we have two independent states for alpha equals beta, and another state is alpha equals minus 2 beta. Now, we can substitute this alpha equals minus 2 beta condition to this circular equation. We find we can pull out the over vector, and we have minus 2, 1, 1 style. The eigenvector that satisfies this eigenvalue equation is 1, 1, 1. And we have the unit normalization can be found as 1 over square root of 3, 1, 1, 1 will be the corresponding eigenvector. And this is a single eigenvalue and a single eigenvector. And in case we have alpha equals beta, then we have, if I substitute alpha equals beta, everything will be the same. We have a 1, 1, 1 style. So this is 1, 1, 1, 1, 1, 1, 1, 1, 1 style. Among those vectors, we have perpendicular component to this one. That is, one example is this one. And the other example perpendicular to both this can be found by taking the cross product of the two vectors. Anyway, alpha and beta relation can be replaced with the lambda relation. The resulting vector is 1/6 for this first equation, and multiplying the normalization factor ma squared that we already factored out, we find the principal value for this eigenvector will be 1/6 of ma squared, and the remaining two pieces will have 11/12 of ma squared for the corresponding eigenvalues. The computation of the third eigenvector can be found in as a determinant form, 1, 2, 3 components, and this is the first element, the components of the first vector. This is psi 1, and this is psi 2 components. The cross product will give the elements for components for the third one. What we have done is 1 cross 2 dot 3 equals a plus 1. So this is a choice. There are many choices, but this is the simplest choice to have right in the school roll. Thus, once we find out the unit normalization eigenvectors, we collect them as a Hermitian conjugate, the first row, second row, and third row. So we find out this is the psi 1 dagger, psi 2 dagger, and copied in here. Psi 2 dagger is copied in here, and psi 3 dagger is copied in here. Then this is the unitary matrix. That means dagger is inverse, right? Unitary matrix. And its inverse is just, we can take the transpose of this and take the complex conjugate. But all these elements are real. The complex conjugate does not make any sense. It is exactly the same as transpose. In that case, the lambda inverse will be just psi 1, psi 2, psi 3 as column vectors. So transpose of this matrix will be in this form. So if we multiply these matrices left and right, what we find will be the diagonalized matrix. And indeed, after all these calculations, what we find is the diagonalized matrix elements. This diagonal form can be achieved by finding out these eigenvectors, list of the eigenvectors in the appropriate way. We can construct a rotation matrix. And all three vectors, we have chosen the three vectors as a cyclic coordinate system, and this is actually the direction of the diagonal from the origin to this vertex. So psi 1, psi 2, psi 3 are all principal axes, and if you rotate about these principal axes, then the angular momentum will be proportional to the angular frequency, angular velocity. Completeness relation can also be reproduced. This is a simple calculation for making use of unit vectors of the Euclidean space and Cartesian unit vectors. And with these non-trivial form of three unit vectors for the principal axis, we can take the direct product and sum over all the three states. The calculation of the direct product will be like this, this, and this. And by summing these three pieces, we find that after tedious calculation, everything will reproduce the identity. This is the completeness relation. Okay. In the calculation, we frequently face the integral over the Dirac delta function. Let us consider in more detail. The Dirac delta function is not a function but a distribution that is only useful for the integration. The functional value itself does not make any big meaning. First, integral over the whole region for the Dirac delta function must give 1. And we can prove that this function is even. That means delta minus x is the same as delta x. Let us consider the integral of f of x. By definition, delta function multiplied by f of x, integration over the whole space of x will be f of 0. What happens if I have minus x in the argument of delta? Then we just replace the change of variable minus x to be t. Then we can replace this x by minus t and this one by minus t. Because this integral goes from minus infinity to infinity, the t integral is from plus infinity to minus infinity. But we have negative sign because this has opposite sign. So absorbing this negative sign into the integral, we can change the upper and lower by exchange the upper and lower bound. Therefore, as a result, the integral can be written in the form with that argument of f is to be replaced with minus t. However, after this calculation, what we find is that f of minus t with t substituted by 0, that means minus 0 is 0, so it's f of 0. So regardless of using delta x or delta minus x, our final result will be the same. That's the reason why the delta function is an even function. A simple application of this even property is delta a minus x should be the same as delta x minus a. This is just, we have put the negative sign on the argument. So this one is the same as this one. The same proof, similar proof can be made using these expressions. Next, we consider the case we have a constant is multiplied to the argument of the delta function. the result is 1 over absolute value of this coefficient and multiplied by a simple delta function. Let's see. We substitute ax, change a variable ax to be t. Then this delta function is expressed in this, and this one is t over a and t over a. We have two cases. If a is a positive, we do not consider the case of a 0. If a is a positive, all this vector comes out as 1 over a, and this upper and lower limit doesn't change at all. However, if a is negative, that upper and lower limit is exchanged. Therefore, if we flip the upper and lower limit, then we have negative sign on it. Therefore, over vector is 1 over a if a is positive. It is minus 1 over a if it is negative. Therefore, it is just 1 over absolute value of a. And then we find that the delta function calculation doesn't care about the over vector, because we have after this calculation we will replace t with 0. Therefore, the final effect is just a multiplication of 1 over absolute value of a. This is the proof for the delta ax is 1 over a absolute value multiplied by the simple delta function. Next, we consider the case when delta function has an argument of a function, and the function has zeros. So xi is a root for this equation. Okay, simple case. We have delta x squared minus a squared. It is factorized, so it is x plus a, x minus a. When x reaches a, the coefficient becomes a constant. It becomes a. So this becomes 2a. When x approaches x minus a, the over vector will be minus 2a. But we don't care about the sign in the argument, so it is just 2a. Now we have constant multiplied by something that depends on x, so it is factored out to have 1 over 2a absolute value. And 1 over 2a absolute value is, we find that there are two roots at x equals a and x equals minus a. So, if we consider the root, if it is 0, we can always factor out x minus xi star, and we have the g, and the g is assumed to be the regular. Then we have delta function constant. So when x reaches xi, then this one becomes a gxi, and that is actually the first order derivative. Substituted x is we replaced with the x equals xi. So the constant coefficient can be factored out after taking the absolute value inverse. Okay, this is the proof for this formula. Next, we consider the physical dimensions of the direct delta function. We remember the integral of delta function over the same variable is 1. Suppose that we have the x is the dimension of length, displacements like that. Then, after multiplication of this dx, it becomes a dimensionless. That means that this delta must have inverse power of length. So the dimension of delta x is length inverse. If x is a mass, then it becomes inverse of mass. Alright, for example, if delta function is function of time and we integrate over time, will result in identity. That means that this delta function is inverse of time. If I have square delta function, delta x, delta y, we have dimension of length inverse, dimension of length inverse, so dimension of area inverse. We have triple product that this three-dimensional delta function appears in the derivation of the Gauss law, and this one has 1 over volume dimension. It is also useful to make use of the Heaviside step function. Heaviside step function is 1 for positive argument and 0 for negative argument. Heaviside step function is also a distribution that is used only for the integral. Therefore, we don't care much about the boundary value. There's a quantum jump at t equals 0. We can use arbitrary value as long as it is finite. It doesn't contribute at all for the integral for the regular function. So, introduction of these two theta function gives that t is greater than a and t is smaller than b. That means the determination on upper and lower bound can be made by putting this theta function as a product to the integrand. Alright, so this one gives integration over t from a to b. By making use of all those methods involving Dirac delta function and Heaviside step function, we can compute this kind of mass distribution. This is massive rod of length L with extremely thin mass distribution, and we can see the density, volume density of this mass distribution is given in this form. First of all, its mass is m. The length along the z direction will be divided in here, and range of z integral is restricted by the product of the theta function, where this one gives a theta z is greater than 0 and z is less than 1. So this one gives a range of integral for z is from 0 to L. Another factor, we have two delta functions. That means x should be 0. This rod is on this z-axis. The coordinate of x and y for the z-axis is x equals 0 and y equals 0. Except that points, all the mass distribution must vanish. Therefore, we have introduced the Dirac delta function, delta x, and Dirac delta function, delta y. Just like what we have discussed, this mass divided by length. However, this density is mass divided by volume. The reason why we need two more factors in the denominator is the introduction of the Dirac delta function. This one becomes identity after x integral. This one becomes identity after y integral. Therefore, the dimension of delta x is 1 over length, and dimension of delta function for y is 1 over length. So this is 1 over area. That means our choice is correct. Choice of the dimension is correct. Let us compute the inertia tensor ij element of inertia tensor by making use of this mass distribution. And we have tensor identical to the previous cases. And one element can be computed. The integral should be y squared plus z squared. The 1, x is missing, y squared, z squared. And we have a Dirac delta function. First, integration over x gives identity. This is the 1. Integration over y gives the y should be replaced with 0. So I substitute y equals 0. Then this one vanishes. Now after x and y integral, we have a single integral over z. That is the integral over z squared. That is 1/3 of L, 1/3 of L cubed. But we have denominator L. Therefore, the final result is 1/3 of ml squared. What about the 2 element? 2 element. The integral should be x squared plus g squared. And here, y integral doesn't change anything, but x integral kills x because of this delta function. Again, the symmetry gives this value for 2 elements will be 1/3 ml squared. What about the 3 components? 3 components has the integrand x squared plus y squared. Because of this Dirac delta function, x squared disappears. Dirac delta function for y, this kills the y squared contribution. Therefore, x33 is vanishing. One, 2, and 1, 3, and 2, 3 has we can factor this x and y in the x integral, y integral. You know, the delta function is an even function from minus infinity to infinity of the odd function. We can also think about it as substituting x equals 0 with 0, substituting y equals 0 with 0. That is true for 1, 2, 1, 3, 2, 3 components. The final result will be 1/3 ml squared 1, 1 diagonal components. Let us consider the inertia tensor when we rotate this rod about the y-axis on the xz plane with a finite angle theta. That can be obtained by coming from the original value and introducing the rotation matrix about the y-axis. We know the explicit form of this matrix in the previous chapter. And the matrix and inertia tensor with normalization is multiplied in here, and transpose is the inverse of that rotation matrix that can be obtained in here. The final result shows that we have 1/3 ml squared and non-vanishing pieces. When theta equals 0, this sine theta becomes 0 and this cosine becomes 1 and reproduces the original value. And actually, even though it is quite complicated, we can compute the inertia tensor for this mass distribution for this appropriate density function. And you can just follow that calculation by substituting this density and repeated use of the Dirac delta function properties. You can obtain these results and these results to find out this one. And the result that we obtained by a rotation of this this rotation gave us this result, but explicit calculation along the very complicated frame of reference, we have reproduced the result. All right. Okay. Wait a second. All right. The first theta function restricts the region of the radius, and second theta function should the radius is less than the original length of the rod. And delta function for y is still the same. However, in the previous calculation we have used delta function for x, but it is not along the z-axis but along the axis that makes the angle theta with respect to z. We know that the equation of this straight line is x cosine minus z sine. You know, the angle between z and this rod is theta. So directional cosine of these two is cosine theta. So that's the reason why I have multiplied sine theta in here. And directional cosine to the x-axis will be sine theta. So that's the reason why we multiplied cosine here and subtracted. Then this one equals 0. This argument equals 0 is the equation of this straight line. And we do the calculation for x integral. Range of x, this is the range of x. This is L, and this angle is the theta, so this is L sine theta. And range of z, this is L, and angle is theta. A right angle is L cosine theta. So range of z is 0 to cosine theta. Range of x is 0 to L sine theta. Alright, so y integral is a trivial. We can carry out the y integration first. After y integration, y becomes 0. Y becomes 0. So the result is only for z squared. After this calculation, we carry out the z integration. No, we carry out the x integration. If we carry out the x integration, delta function coefficient was cosine theta, right? And this result is actually the absolute value of the cosine theta after integration. So we have absolute value of the cosine theta in here. And then, what's next? Alright, we have z squared in here. Z squared, we have L 1/3 L cosine theta cubed. We have absolute value in here, and we have cosine theta squared. All right. we assume that theta is between this 0 to pi, 1/2 pi. Okay. 2 element. In the calculation of 2 element, we have x squared plus z squared. In a similar manner, we can carry out the calculation for this 2 element. Our final result will be 1/3 ml squared. 3 free elements do the same job. Final result is 1/3 ml squared sine squared. And you can follow this calculation by yourself. As the next step, we consider the eigenvalues of this matrix. We know that eigenvalue is invariant under similarity transformation, so it is somewhat stupid to calculate it again, but we check if it is true explicitly. We have the matrix after rotation. Let us make use of this to find out the secular equation. The secular equation states that the determinant must vanish. The determinant can be computed in this way, this vector, and remaining pieces we have 2 by 2 matrix, and the second one vanishes. The third one minus CS appears, and the matrix, this 2 by 2 matrix, appears in here. This determinant is this 1 minus lambda, sine square minus lambda, minus CS, and this is 0, minus 1 minus lambda, and minus cosine sine, and this direction is odd parity, minus sign appears, therefore we have positive sign. And then 1 minus lambda can be factored out, and this one multiplied by this one is in here, and this one multiplied by this one is in here. Expanding the inside the brackets, we have lambda squared and minus cosine squared plus sine squared lambda, and constant piece is cosine squared sine squared subtracted by cosine squared minus sine squared. So they cancel. We can factor this lambda out, so it is we have lambda minus 1, and again sine squared cosine squared is 1, so lambda is 1 squared. So this is doubly degenerate state. When lambda equals 0, if I substitute lambda equals 0, what we find is cosine squared sine squared. The corresponding eigenvector is a sine 0 cosine. And here, if I substitute lambda equals 1, we have these pieces. The trivial one will be y equals 1, and the other pieces vanishes. So this is the choice for side 2. And the choice for side 1 with orthogonal to this, then means we have these 2 components, and these 2 components have a cosine sine minus sine, and all these 3 are orthogonal. In summary, in this situation, we have 3 axes that they are called the principal axes. The eigenvectors of this matrix are called parallel to the principal axis. Once we choose these principal axes to be x, y, z axis unit vectors, then the matrix is diagonalized in this way, because the corresponding eigenvalues are listed in the same manner. We recall that the eigenvector psi 1 is cosine 0 sine, so Hermitian conjugate. And the second one is 0, 1, 0. The Hermitian conjugate is 0, 1, 0. And third one, Hermitian conjugate is sine, 0, cosine. Listing these three row vectors in this way, we construct the diagonalizing matrix lambda. And its Hermitian conjugate, Hermitian dagger, is obtained by taking the transpose and by taking the complex conjugate. Because they are real, it is just like the transpose. So it is a unitary and orthogonal matrix. We multiply the lambda and its inverse transformation to the complicated structure of this original coordinate. The final stage will find the diagonal matrix that reproduces the eigenvalues. Okay? Now we consider the change of variable by making use of the Dirac delta function. Suppose that we have two generalized coordinates that reproduces x1 as the Cartesian coordinates. However, this is the original integral involving x1 and x2. We can compute the Jacobian to find out the integral is in this form. However, Dirac delta function can be used without abiding by the without resorting to the determinant. First, we multiply identity. This is delta function for Q1, and this is delta function for Q2 integral. We insert this identity, unity, twice. Then, what we find is dx dx2, this integral. This is integral, original integrand, and the product of delta function integrals. Now, we leave this Q1 and Q2 integral out, unintegrated. Instead, we integrate over x1 and x2. So, move these two integrals inside to carry out the delta function integration. First, we compute the x2 calculation. We find that x2 appears in here. So this value is just identity. And after this calculation, what we find is x2 equals q1 minus x1, because this one equals 0 means x2 equals q1 minus x2 equals 0 means x2 equals q1 minus x1, right? And then we integrate over x1. Now, because we have replaced x2 with q1 minus x1, we also have to replace this x2 in here with q1 x1. But we find this value is q2 minus q1 plus 2x1. So we have to carry out x1 integral, but delta function has an argument of x with factor of 2. Then the integral becomes 1/2, inverse of this coefficient. Therefore, we have over a vector that is actually the Jacobian, and q1, q2 integration, and x1 and x2 are replaced with this delta function conditions. That is 1/2 q1 minus q2, 1/2 q1 plus q2. This method can be generalized to be applied to a more complicated case, that is the 2D polar coordinate system. If we carry out the integral over 2D polar coordinate system from the Cartesian coordinate system, we can also make use of the Jacobian method, but without resorting to the Jacobian method. Let us compute this one directly by introducing the simple unity factor. We have x equals r cosine and y equals r sine theta. That can be done with the theta integration. Theta runs from 0 to 2 pi, so it covers the whole space. However, arctangent can be introduced. However, arctangent has a period of pi, so it repeats when we rotate the 2 pi. So we need to make use of arctangent twice. But first arctangent is in the region, in this positive x region. And then second arctangent has second and third quadrant. The difference between these two is a phase difference by pi, 180 degrees. And we have condition, x is positive, x is negative. Except that these two contributions have the same contribution. However, this is pi, so whole region should be considered in this way. Second factor is integration over r for the delta function of radius. This delta function can also be expressed as a 2r over r, and this 2r can be moved inside, and this one can be factorized. So you know r is positive. It does not touch the this delta function at all. So it can be replaced with r plus square root r squared plus y squared, and then it's a more simplified form, delta function r squared minus x squared minus y squared. Now, let us compute the delta function integral not by theta but by Cartesian coordinate y. If I do this integral, what I need to do is find out this value. That is y equals x tangent theta. Theta x y. Y must be the x tangent theta. However, this one has a simple structure, but what I need to do is to find out the derivative, first order derivative of this and inverse of the reciprocal of this. So let us compute the differential, the derivative with respect to y. Arctangent is 1 plus something squared, and the derivative with respect to y is 1 over x. So as a result, if we multiply x squared, both numerator and denominator, we have x over x squared, y squared. Reciprocal of this is x squared plus y squared over absolute value of x. After this y integration, y should be replaced with x tangent theta. Alright? And this one is always identity. It's a positive and negative, but x is either positive or negative, so this is just identity. And after this delta function integral over y, we can substitute y equals tangent theta, and that is a factor x squared to factor out, and 1 plus tangent squared theta is a cosecant secant theta. So cosine squared theta in the denominator, and over factor is absolute value of x. Now our dependent Dirac delta function is to be integrate over x. If we integrate over x, because what we have done is a y integral already, so y should be replaced with the x tangent theta. Then it becomes a square root x squared over cosine squared. Square root means absolute value of x and the absolute value of cosine theta. As we know, the radius is a positive definite. This one can be replaced with x over cosine theta with the condition that theta function, this x over cosine theta, must be positive definite. right? So after this x integral, we have over vector cosine theta outside. However, we have introduced that this one is positive. Therefore, its absolute value of cosine theta remains. As a result, integral over Cartesian coordinate is replaced with this integral over r and theta. So x integration or y integration can be carried out, and the previous result was like that. The final result cancels cosine theta dependence and keeps the remaining pieces the r-dependent single factor. That is the Jacobian in the 2D polar coordinate system. We can generalize this method to the three-dimensional polar coordinate system, and the detailed calculation is given in here. We have r integral and cosine theta integral and phi integral. This phi integral is the same as the 2D polar coordinate system. Detailed calculations are given in here. And you can, I hope, you can follow this calculation to find out the Jacobian r squared, and angle is the azimuthal angle, runs from 0 to 2 pi, and polar angle, cosine polar angle runs from -1 to +1. Alright. In summary, mass density can be simplified for the special cases by making use of the Heaviside step function and Dirac delta function. There is a great simplification for the calculation. And regarding the dimensions, delta function of length has a dimension of reciprocal of length. So product delta function is a reciprocal of area. And at the end of the day, we'll find that density should be mass divided by volume. Equipped with those methods, we can compute the inertia tensor for a disk using this distribution, and computation is already made in here. You can follow the calculation, and all of the components can be computed, and this is the final result. We can compute the case when the normal direction is not z-axis but n hat, and hat is given in this form. So in that case, we can find the rotation matrix to find the x prime, y prime, and z prime. That can be computed in this way. Using the rotation property directional cosines, we can construct a rotation matrix that transforms this disk from the original xy plane to this direction. By making use of this rotation matrix, we finally obtain the matrix elements in this general direction. Sure, we can solve the eigenvalue problem for this case where z is replaced with n hat, the diagonal direction, and at the end of the day we will find the principal axis, and that principal axis along the z direction, and the remaining piece will be on the disk. Okay, so our method of introducing the Dirac delta function and Heaviside step function was quite useful to compute the special cases.